Hello, Mr. Claudia here. Before we go any further in our study of trigonometry, we have to talk about something called the radian. You've probably come across the radian before and you thought it was a neat concept that was going to come and go. But actually the radian is central to everything we do with trigonometry. Even though you've used degrees for most of your math career, radians is definitely the preferred choice for when we're talking about trigonometry and trigonometric functions. So this is the thing we have to get very, very comfortable with. So let's just do a quick review of radians and we'll look at some difficult examples. The way I introduce radians is I ask this question: what is the length of this line segment? To do that, I get out my ruler and I measure, and oh yeah, it's about, what did I get on this old ruler? 3.5 centimeters. However, centimeters aren't the only way to measure a line segment. If we were to go to the United States, they wouldn't know what this means because they're one of 3 or 4 countries in the world that still use the imperial system of measure, which uses inches and feet. If I were to measure this in inches, what do I get? Well, this is 1.5 inches, is 1 1/4, so about 1 3/8. So 1 3/8 of an inch. Us living in Canada, a little FYI, like, you guys have to be comfortable with both of these, right? It's not enough to just know centimeters and say, oh, the metric system is all I care about, because the reality is the huge country to the south of us, it's 10 times our size. That's our biggest trading partner and source of materials and greatest ally, uses this. So you have to be comfortable with this too. And in fact, if you go into the Home Depot and you're buying screws to make something, you're gonna have to know the size of those screws in inches. But the point, anyway, digression aside, there are 2 methods or 2 units for measuring length. That's my that's talking about length, but that's my introduction to the radian. Radian is an alternative unit for measuring angles. And you should take a step back and think, like, how do we measure angles again? Oh yeah, we use degrees. But why on earth would we have chosen to measure angles in degrees? Like, why are there 360 degrees in a circle? Isn't that an odd number? Wouldn't it be better to make like 100 degrees in a circle or 500 degrees in a circle? Wouldn't that have been a better number? In some ways, 360 degrees is a lot. It's kind of arbitrary, and TOK. Let's just take a side steps to the side here. The reason we use 360 degrees is because circles and a lot of this kind of ideas were developed by Babylonians, which use a base 60 counting system. So it's a little TOK. We, by the way, use a base 10 counting system. So you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you have a placeholder. Then you count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you have 2, and you kind of count up that way. In Babylon, they did a little different, so they would count to 60, and then that would be placeholder 1, and then you count to 60 again, placeholder 2. So it's a little bit different. But the remnants of this exists all over our life. Like if you have the 60-second minute, the 60-minute hour, 360 days in a year, all of these things are kind of base 60. And so that's where we get the 360 degrees in a circle, which again, is sort of arbitrary. It's as arbitrary as saying the length of your foot is 1 foot, right? It's just what defines these things. So all mathematicians have said, let's define a better measure of an angle. What would be the best way to define an angle? Well, we would define the angle as a relationship in a larger circle. So for example, well, actually we'll give you the definition of a radian. A radian is the size of the central angle subtended by an arc which is the same length as the radius of the circle. So it's a little bit of math mumbo jumbo there. It's a little bit easier to understand this as a diagram. If I have a circle and it has a radius of r, well, if I drew, cut out a piece like this, so both of these sides are r, and the length of the circumference is also r, we're going to call that 1 radian. How rad. this seems a little goofy. Like, what's the point of this? I mean, what is this? So then if I had a length that's 2 radians, so somewhere here, remember this is 2 radians now. This would be 2 rad. It sort of seems like a weird way to count. Like, what is this? What does this mean? And why does what is 1 rad? What is 2 rad? The reason why we like to use this definition is it really is rooted in the formulas for circumference of a circle, and as we'll see later, area of a circle. When this really becomes obvious is when you have 180 degrees. So you start here. Remember, this is length r. And then we're going to have it go all the way out here, which is, again, this is length r. So now my angle that's subtended here, well, let's look at, so in this case, if I go 1 radius along the circumference, that's 1 rad. If I go 2 radiuses along the circumference, that's 2 rad. Here, if I'm going 180 degrees around, okay, well, this is half of a circumference of a circle. Remember, the circumference of a circle is 2 pi r. If this whole length is half a circumference, that's equal to half 2 pi r, or just pi r. So really, when I go this far around the circle, I'm not traveling 1 radius, not 2 radius, I'm traveling pi radius. If I've gone pi radius across, then I've gone pi rads across. So there's this relationship between the circumference of the circle and the angle. If you go 1 rad, you've gone 1 radius, which is a really kind of hard to imagine, but it makes a lot of sense if you think of it as fractions of a circle. So if I go 90 degrees, well, that would be a quarter of pi. So this would be a quarter rad, pi. Sorry, I'd gone half of a pi. So this would be the angle here is half pi by 2. You can see all the different radians of note, and they're all expressed as fractions, which is a lot easier. That's what we see in this example. We don't usually say 1 rad or 2 rad. We usually are talking about fractions. So the easiest way to remember rads is 180 degrees, that's pi radians. So then you can look at fractions. Well, 90 degrees, half of that is pi by 2. If you want to go 45, half of that would be pi by 4. 60 degrees, that's 180 divided by 3, so it's pi by 3. So you kind of can start to build this up. So you have pi by 6, pi by 4, pi by 3, pi over 2. Now to get to 120, I'm adding an extra 30 degrees, so I'm adding a pi by 6. So that gives me 4 pi by 6, or 2 pi by 3. Similarly here, to get to 135 degrees, I'm taking 90 degrees, I'm adding another pi by 4, so I'm getting 3 pi by 4. You can see this as fractions, or as fractions of a clock almost. Here you have pi by 6, 2 pi by 6, 3 pi by 6, 4 pi by 6, 5 pi by 6, 6 pi by 6, which is just pi, 7 pi by 6, 8 pi by 6, 9 pi by 6, etc. You have to get really used to this. Like I said, you have to be able to use the two interchangeably, and if anything, radians are going to become more common in your life. What you probably were shown when you first learned radians is how to convert, and this is not something that comes up very often, but it's the first thing we teach you. How do you convert between the two? Well, as long as you can remember that 2 pi is equal to 360 degrees, or I even like this better, pi is equal to 180 degrees. Then you just multiply in a way that will eliminate the units. So for example, if I have 1 rad, well, I multiply by 180 degrees over pi rad. Now the rads cancel out, and so my answer is going to be in degrees. I need to use a calculator to do this math. It would be 1 times 180 divided by shift pi. Oh, no. 1 times 180 divided by shift pi. And that gives me an answer of 57.3 degrees. Similarly, if you want to go from degrees to radians, you multiply by the pi and 180 degrees. You might have to be confused about which one goes on top. Well, again, you want the degrees to cancel out, so you want them one on top, one on the bottom. So it's 1 times pi rad divided by 180. 1 times pi rad divided by 180. And you end up with 0.0175 rads. So, and again, this is not something you're going to do very often. It's kind of an impractical thing. But essentially, 1 radian is 57 degrees. So 1 rad, again, is not a super useful measure. It's all about expressing rads as a fraction of a circumference. And similarly, 1 degree is a very, very tiny radian amount, right? Because there's only, in one full circle, there's 2 pi radians. So that's about, what's 2 times pi? 6.28. So there's only 6.28 radians. So you can imagine 1 degree is a very, very small number. Okay. Anyways, hopefully that's a bit of an introduction to radians, and hopefully that'll help make things clear enough for what's going to come now. So assume, it's in bold letters, assume that all angles and trig functions are in radians. Unless it's written, unless you explicitly see a degree sign, you're looking at radians. And that's important to remember. Because all of your calculations could be messed up if you don't consider this. So now let's revisit everything we know about trig. First of all, our special triangles. Remember this one? 1, 1, root 2. You draw it by drawing an isosceles triangle with length 1. You can figure this out as root 2. The lengths don't change. Now the angles are different though. Instead of 45 degrees, this is pi by 4. So now it's really easy for me to figure out what tan pi by 4 is. Tan is opposite over adjacent, which is 1 over 1, which is just 1. Make sure you memorize these, right? We need to know our special triangles. This second triangle, the 1, 2, 3, it's easy as 1, 2, root 3. You take a equilateral triangle with length 2. You split one length in half, so you have 1. This is root 3. This is the 60-degree angle, or pi by 3. This is the 30-degree angle, or pi by 6. Now, if I want to know sine pi by 3, remember, pi by 3 is basically 180 degrees divided by 3, so it's about 60 degrees. So it's this angle. Sine is the opposite over the hypotenuse. So that would be root 3 over 2. Those are both, that's an exact answer, right? That's without using your calculator. If you are using your calculator, make sure you're doing this correctly, right? If you're in degree mode and you type sine, you're doing this shift pi divided by 3, you're actually going to get the wrong number, because if you're in degree mode, you can see the little d here, you're actually finding the sine of an angle. What's pi 3? So you're finding like the sine of 1 degree, basically, sine 1.2 degrees. That's not correct. That's not what this question is saying. You're in the wrong mode. So make sure when you're doing calculations, you're correct. You change your calculator correctly. You press mode until you get to degree or radians, and you press 2. There's a little R there. This is the frequently made mistake of my grade 10 students when they first teach them trigonometry. Now, if I were to type sine, and I were to go shift pi divided by 3, I would get the right answer. That is root 3 over 2. So let's make a note of that. When using a calculator to find an approximate answer, ensure the mode is correct. Degree or radians. And we saw it, sine pi by 3 is equal to 0.866. That should be use rad mode. So that's just a point to be very careful about. Okay, let's train a Lapage. On the back of the page, you're going to find a few concepts that are overly emphasized in IB. So these are things you might have seen, you probably didn't, You'll be very shaky with them. They're going to take some time to learn, and they are very emphasized in IB geometry questions. So these have to do with arc length and sector area. And they use the radian concept just beautifully. So for example, what is the length of the arc AB? So this length L. I mean, how would you calculate that? That's like a curved line. You couldn't even measure it with a ruler if you asked. But just like we talked about radian being a fraction of the full circle, this length can be thought of as a fraction of a full circumference. So you could think of this ratio of arc length to circumference. So this length in terms of the total circumference. So length and the circumference of a circle is 2 pi r. And that ratio is going to be the same as this angle, the subtended arc, or the radian, or the subtended angle, or the radian measure, as a fraction of the full circle, which I know is 2 pi radians. If you cross multiply, you're going to get 2 pi L is equal to 2 pi r theta. If you rearrange that for L, you're going to get L is equal to theta r. And this is almost a direct, application of the idea of a radian. But now to find the length of an arc like this, you just take the angle in radians, that is, and multiply by the radius. It's super easy. So for example, if I wanted to find the perimeter of this sector, the sector is a kind of a piece of pie or a piece of pizza that you've cut out of a circle. This one has radius of 4, radius of 4. It has a length here which is equal to which is equal to theta r. So the perimeter is going to be 4 plus 4 plus, so 4 plus 4 plus theta r. So that's going to be 4 plus 4 plus theta is 1.3 rads times the radius, which is 4. So I take my calculator and I have 1.3 times 4 plus 4 plus 4, and that gives me 13.2. Note that you don't have to have your calculator in rad or degree mode when you're doing simple adding and subtracting and multiplying. The radian and degree mode has to do with when you're doing the sine buttons, the cos buttons, the tan buttons. So that's one concept. Again, it seems easy enough, but you're going to get some more challenging questions involving lengths along a circle like this. The other application is if you were looking at a sector area. So remember, sector is that piece of pie that's been cut out of, been cut out, or a slice of pizza. We call this a sector. Let's call it sector A in this case. Okay, the sector, just like we imagine here the length as a fraction of a full circle, the sector area can be imagined as a fraction of the full area of the circle. So this area of the sector, let's call it sector area A, over the area of a circle, which is pi r squared. Well, that fraction is the same as the fraction of this angle in radians, A, or theta, over the entire angle, which is 2 pi. Again, if I cross multiply, I get 2 pi A is equal to pi r squared theta. If you rearrange, I get A is equal to theta r squared over 2. That is my area of a sector. Again, you haven't seen it a lot, but it's very powerful. Because now if I give you a question like this and said, hey, find the this angle and find the area. Well, I could use this formula to find the area. I need to know what the angle is though first. How could I find the angle? Well, I know what this length is, I know what the radius is, so I can actually use my arc length formula. 8.4 is the arc length, theta is what I'm trying to find, my radius is 5. If I rearrange and solve, I get 8.4 divided by 5. That gives me 1.68 rads. Remember, these formulas only work if you're using radians. Now to find the sector area, I use the formula theta r squared over 2, which is 1.68, just a straight number, times 5 squared, that's the radius, divided by 2. So I get 1.68 times 5 squared divided by 2, which gives me 21 centimeters squared. So should we make a note? These formulas only work for radians. These formulas only work for angles in radians.
No.
Okay, let's do one last example now, and this will give you an idea of how these two pretty easy concepts and pretty easy formulas can really make your life a little bit miserable. So I have a question here. A sheep is tethered to a post which is 6 meters from a long fence. The length of the rope is 9 meters. Find the area which the sheep can feed on. It's very practical. Probably, you've come across a problem like this in your life before. So I have a fence, and you have to imagine I have this post. I'm going to draw this thing a little smaller. And so this is 6 meters away. But they have a 6 meter long tether. So if you can imagine, we know that the sheep can eat all over here, but then eventually it could get like the furthest away, right? The furthest away that it can walk is 9. And then actually it can only ever be 9 meters away. So if you want to imagine this, it's actually a circle. And then similarly here I have 9 meters away. Not the best drawing, to be sure. But that area oh boy, terrible drawing. It's going to live forever on the internet. But that pi, that amount of pi is going to represent the area that oh, there's 9. The area that the sheep can graze. Actually, oof, I drew it incorrectly. Okay, I'm going to have to wipe this out. Oh boy, not good. Okay, so we're back. How embarrassing. The mistake I just made a correction here. So this is where the sheep is tethered. So this is this huge area that the sheep can eat the grass. It's this whole circle, but then in this portion, it's actually cut off by the fence. So it's not quite a circle. Like you can imagine the circle, if it was the entire circle, it'd be really easy. I would just use the area of a circle, but this is not. I need to actually remove this bit. So what I need to do then is, what I'm essentially doing is finding this area of the Pac-Man and then adding the area of this triangle and the area of this triangle. But to figure that out, I need to know this angle. I need to know to be able to find the area of this sector, and I also need to know the this angle to find the area of this triangle. So there's a few angles I need. Let's start by finding this angle here. We'll call it angle alpha. It's actually the same in both cases. So let's say cos alpha. Remember, this is a right angled triangle, so alpha is going to be adjacent over hypotenuse. Cos alpha is going to be adjacent over hypotenuse. If I type that into my calculator, I mean, this is a ratio. It's a published ratio. We should, if I type 6 divided by 9, I get the ratio. It's 0.6667. Okay, now if I want to find out what the angle is, I have to use the inverse cos, or the cos -1 of 0.6667. Make sure when you do this, shift cos, that you're in radians mode. Otherwise, you're going to have a wrong answer. That's correct. Alpha is equal to 0.841. Does this number make sense? Well, the angle is not quite 57 degrees, right? Remember, 1 radian is 57 degrees, so 0.8 radians is probably like 40-something degrees. So that seems okay. So now this angle, which I need for the sector, let's call this theta. This theta is going to be a full circle, 2 pi minus 2 alphas here. So that's going to be 2 times shift pi minus 2 times answer equals, and I get 4.601. Remember, we're always keeping a few extra, at least one extra decimal place, so or a significant figure. So I have 4 significant figures here. So really important here that all angles are in rad. So now I know these angles Now it's really neat. I can find the area of this shape by using kind of this idea that the area of the blue is the area of the sector, that is the area of the Pac-Man, plus 2 times the area of the triangle. Right? Plus this triangle, plus this triangle. So what's the area of a sector? Well, that would be theta r squared over 2. And what's the area of a triangle? Well, here's where it gets neat. We get to use that formula that we developed a few sections ago. Half AB times the sine of the angle in between them. So what is my theta? It's 4.601. What is my radius? It's 9 squared. What is plus 2? Divide by 2. Plus 2 times half. Okay, for this triangle, I know this length, and there's an angle between them. So I have 6 times 9 times sine 0.841. Oh, I didn't keep 3 significant figures there. Not great. Okay, so now I just type all this into my calculator. Make sure you're in radians, and you get this final answer. 227. It's an area, so it'd be meters squared. So there you go. You can have some really tricky problems. This would not be easy to do without doing some practice of this. You can see that these aren't hard concepts. It's not hard algebra even. It's just a concept that you haven't really done before. So with that note, what homework can you work on for this section? Where can I write it? How about up here at the top? We're going to be doing for homework page 397, numbers 1 to 5, and page 393, number 1 to 7. Make sure that you use your calculator to do this. So these are those word problems like we just saw, and those I really recommend doing. Good luck with that, and we will see you next time.